Okay, this is the first video of the lecture for Chapter 1, and we're going to cover the ideas of computer science, abstraction, and the abstract data type. And there's quite a bit there, although in the next series of lectures we'll be covering the Python programming language, which will take us a couple of weeks to cover. So first about computer science, because computers have become more and more complex, and we're solving larger and larger problems, and actually more difficult problems, computer science is becoming more and more important to solve problems. In fact, you'll see problem solving in computers is now integrated in almost every level of science and becoming more and more important to actually making advances in science these days. Uh, Now, computer science, the science part is to have a way that we can create repeatable foundations and principles to be able to apply those principles to problems. Now, you have already learned how to develop a program given a problem statement. So in intro class, we give you a lot of here's something to write a program that does this, and you write a program that does that. And so basically, you've taken a problem statement and you've been able to write a program. Now, when you get into larger programs, you have to start to develop more of a systematic way of doing that. So in larger programs, there's a whole science of how do you break down the problem statement and identify what parts of that apply to the program. And we're not really going to get into that. That's more of an advanced software engineering problem. And you also learn some of that in the IT area of how do you solve problem solving. Now, you also learned that programming can be quite hard and involve a lot of complexity. And there's just a lot of detail and knowing the syntax and the rules of a language that you have to learn. Now, you've already been through that once for a language. It turns out a lot of those things you've learned you can apply to a new language, and that's what we're going to do. And as you learn more and more new languages, you're not really afraid of learning some new language anymore because you've got a good solid foundation for jumping into any new language. But there are some fundamental ideas that can be related to both the problem-solving process that can be used to help. So during this class, by looking at how certain problems have been solved and worked on by a lot of computer scientists, you'll start to build some foundational ideas you can apply to problems that you didn't have before. So two important things in this chapter is a review of computer science and the study of algorithms, which we're doing in this slideshow, and how data structures fit into that. And then we're also going to spend a lot of time on learning the Python programming language. And we're not going to learn the whole language, but we are going to learn a bit more than what's in the book. We're going to give you some extra material on object-oriented programming and a little bit on functional programming. Now, algorithms, which are basically developing a step-by-step list of instructions to solve a problem, so this is kind of the scientific approach to problem solving, has been around for a really long time. In fact, the first algorithms are dated back to 300 BC. And the thing about an algorithm is once you have a step-by-step way of following some instructions to solve a problem, you can teach people to do that. So with the advent of writing, this is important to write down how to solve certain problems. And so this became the first algorithms. Now, of course, computers came along a lot later. We primarily still look at how do you do algorithms, but it's within the context of eventually realizing it on a computer. But basically, in computer science, you're studying algorithms. Now, the study of solutions to problems, as well as the study of the problems with no solution, turns out to be part of computer science. We're not really going to look at the problems with no solutions in this class. And that's the problem of whether something is computable or not computable. Everything we're going to be doing in this class is a computable problem. We might mention as we go some problems that are not realistically computable, but there are actually some problems that can be proved that there can never be a solution to them. Now, CS is also the study of abstraction. So we're going to see that a lot of what you do in programming is abstraction, so that rather than writing the specific steps for a computer to do something, you're going to rely more on people that have written those steps for you, and they've abstracted their work so you can use it easily with just a simple interface. So in abstraction, let's talk about controlling an object. We're going to see there's two types of main abstraction in a bit. And in object-oriented programming, this is kind of how you approach object-oriented programming. You deal everything as an object, and you have certain control over that object, and we're interested in the perspective of how you control that object. So they use the example here of an automobile. Now, when you're a driver, you have to learn the controls for an automobile, and there's not that many of them. And once you learn those simple set of controls, you can control the automobile. Now, the automobile is very, very complex mechanical device. If you become a mechanic, you would learn a certain level of that device, but even then, you get into the computer systems inside it, some of the submodules, and you'd have to go to the fact that makes those to understand what they do. So actually, an automobile is levels and levels of abstraction. Meaning that you, as the automobile driver, only have to know a certain number of controls, and that's an abstraction because you can control the entire car with just those controls. You use those controls, it does what you want, and that's it. You get into any other manufacturer's cars, they have the same set of controls, and that's also important, where you duplicate the same set of controls across all cars. So there's a lot of these controls are standardized, and that's going to be similar to what we're going to talk about with abstract data types. So we call the set of controls to control something like this your interface. So an interface is just basically a list of the controls, probably what they do. So here's an example of an interface that's part of Python, and this is similar to what in Java or C++ you had functions. You could call a function to give you the square root. So here in Python, you can call a function to give the square root of 16, and it prints out the result. So somewhere someone has written this function which has computer code inside of it. We don't know what language. Doesn't matter. We don't know how it actually computes the square root. We don't really care. We just want to know that it works for us, so that it's an abstraction that works all the time, and we can rely on it. So you can think of the square root function as a black box, and you call it with n, and it returns the square root of n. Now in your intro class, you actually wrote functions or methods that you passed parameters and it did something, so you actually wrote all the code. But once you had that function defined, you could add it to a library and other people could use it, and as long as it worked correctly, they wouldn't have to know what code you put inside. As long as it wasn't too slow, or it didn't use all the memory, or it worked in all the numbers they expected, as long as it met the expectations, then they could use it. So that whole issue of boxing your code inside of this name thing is called a procedural abstraction. And procedural abstraction is primarily what your previous class was about when you studied functions and methods. So what is programming? Well, programming is the process of taking an algorithm and encoding it into a notation, which is a programming language, so that it can be executed by the computer. Computer science is actually not the study of programming. Sometimes there is a whole area of computer science which studies programming languages, but it's not really the study of actual programming. It's the process of developing algorithms. So that's going to be what's important. So programming is an important part of computer science. We're not saying that you're not going to be programming, or you don't need to know about programming, but it's not the end all. It's like if you're a writer, it's important that you know English and you can put sentences together, and you do that all the time in writing. And different writers write in different languages, but writing is not about that part. So programming is how we implement a working representation of our algorithm, and it's actually programming is much more creative. Just like writing is creative, programming is creative.